Hello everybody, welcome to my channel VKS Chem Tutorial. You know the different types of organic reactions are addition reactions, elimination reactions, substitution reactions and rearrangement reactions. Among these, I have already uploaded a video about elimination reactions. Among the substitution reaction, I will discuss nucleophilic substitution reaction in this video. You know, a substitution reaction is a chemical reaction during which an atom or one functional group in a chemical compound, usually substrate molecule, is replaced by another atom or functional group. See, nucleophilic substitution is a class of reaction in which a leaving group is replaced by an electron-rich species that is usually referred to as nucleophile from a substrate molecule. That is, leaving group is departed from the substrate molecule along with the substitution of the electron-rich species called nucleophile within the substrate to produce product. See, it is the nucleophilic substitution reaction, general nucleophilic substitution, general representation of nucleophilic substitution reaction. You can see the nucleophile with its lone pair of electron attacks the substrate molecule. From the substrate molecule, the leaving group departed and to form the product. It is the general nucleophilic substitution, general representation of nucleophilic substitution reaction. The electron pair from the nucleophile attacks the substrate, forming a new bond in the product, while leaving group depart with an electron pair. That is why the principal product here is RNU. There are two fundamental events in a nucleophilic substitution reaction at an sp3 hybridized carbon. The first is breaking of the sigma bond to the leaving group. Sigma bond between the carbon atom of the substrate molecule and the leaving group gets broken in the first event. And in the second event, formation of new sigma bond with the nucleophile. The substrate form a new sigma bond with the nucleophile. According to the time lag for this process to happen, the nucleophilic substitution is classified as SN2 reactions, that is substitution nucleophilic bimolecular reaction, and SN1 or substitution nucleophilic monomolecular reactions. Okay, first of all, we will discuss nucleophilic substitution, that is bimolecular reaction, and is represented as SN2 reaction. Nucleophilic substitution bimolecular reaction, that is SN2 reaction. The mechanism of nucleophilic bimolecular reactions, that is SN2 reaction, involves bond breaking and bond formation occur at the same time. That is very important. Bond breaking and bond formation occur at the same time. Here you can see it is a one-step process. Nucleophile attacks the substrate molecule. Bond breaking and bond reformation takes place in a single step, forming the product. Here you can see the carbon, the bond between the carbon and the leaving group first broken. At the same time, the bond between nucleophile and the carbon in the product gets formed. Both these process takes place simultaneously. Here, both the nucleophile and the substrate molecule take part in the reaction. It is a single step concerted mechanism. That means the bond breaking and bond reformation takes place simultaneously in a single step reaction, and hence it is a concerted mechanism. And you can see the nucleophile and the substrate molecule both are taking part in the reaction, and hence the rate of reaction can be represented as rate is equal to K, the rate constant, into the concentration of this substrate molecule that is represented here Rx, and the nucleophile. It is X in the, Nu, the nucleophile in this reaction. And so the rate can be represented as rate is equal to K into Rx, that is substrate molecule, and the nucleophile, the concentration of Rx and the concentration of nucleophile. And so it is a second order reaction, and hence it is represented as second order rate equation. This equation is otherwise represented as second order rate equation. Okay, that is the mechanism of SN2 reaction. SN2 reaction is a single step reaction. It is a concerted process, and both the bond breaking and bond reformation takes place simultaneously. First of all, the nucleophile attacks the electron deficient carbon atom. Simultaneously, the bond between carbon and the leaving group gets broken and form a new bond with the nucleophile. This carbon form a new bond with the nucleophile in the product. All this process takes place in a single step and is called the concerted mechanism. And the rate equation is a second order rate equation because both the nucleophile and the substrate molecule take part in the concerted mechanism of SN2 reaction. Okay, the mechanism of SN2 reaction actually involve a transition state where the nucleophile is in the process of formation of a bond with the electron deficient carbon atom of the substrate molecule, while the bond between carbon and the leaving group is in the process of departing from the electron deficient carbon atom of the substrate molecule. That is the transition state of SN2 reaction. For example, here when the nucleophile OH negative attacks the substrate molecule methyl chloride, this carbon atom of the methyl group is electron deficient, and this nucleophile attacks the electron deficient carbon atom. When it takes place, at the same time the leaving group halogen here departs, and during this process actually a transition state, we can assume a transition state in the SN2 reaction where the nucleophile OH is in the process of formation of a bond with this central carbon atom or the carbon atom of the methyl group, which is electron deficient in nature or electrophilic in nature, and the carbon halogen bond is in the process of detaching or departing. Chlorine is in the process of departing from the carbon atom, or the bond between the carbon halogen is in the process of detaching, and such a state is called the transition state. And these three bonds, carbon hydrogen, all the three carbon hydrogen bonds are placed in a single plane, and it is planar, and this transition state is highly unstable because you can see the central carbon atom bearing 5 bonds, 3 full bonds, full covalent bonds, while the 2 are partial covalent bond, and hence this state, which is called a transition state, is highly unstable. It decomposes, forming the product methanol. Here methanol is formed. Okay, and it is the actual mechanism of SN2 reaction. That is, nucleophile attacks the substrate molecule, forming an unstable transition state, which decomposes, forming the product. All this process takes place synchronously or simultaneously. Bond formation and bond breaking and bond reformation takes place simultaneously in a single step, and it is the mechanism of SN2 reaction. Okay, another important example of SN2 reaction is the reaction between methyl bromide and methyl acetate. Here, the methyl bromide with the nucleophile acetate affords the substitution product methyl acetate with the loss of bromide as the leaving group. The rate of the reaction depends on the concentration of both the reactants, that is nucleophile and the substrate molecule. That is why the rate equation is second order. This bimolecular reaction involves, as in the previous case, a one-step mechanism in which carbon halogen bond is carbon halogen bond is broken. Simultaneously, carbon nucleophile bond is formed. See the reaction. Here it is methyl bromide. That is a substrate molecule. Acetate ion is the nucleophile which attacks this carbon atom of the methyl group. Thereby, methyl acetate is formed. Bromide departs from the methyl bromide. That is the leaving group. Bromide is the leaving group. You can see both the reactants appear in the right equation. That is why the right can be represented as right is equal to K into the concentration of methyl bromide CH3 Br into concentration of CH3CO negative, that is acetate ion. It is the product of concentration of methyl bromide and the acetate ion. That is right is directly proportional to product of concentration of methyl bromide and acetate ion. That is why it is a second order, it follows a second order kinetics, and hence it is an example of SN2 reaction, right? Now let us see the stereochemistry of SN2 reaction. See, it is the mechanism of SN2 reaction. In a backside attack, the nucleophile approaches from the opposite side to the leaving group. Here it is bromide of the substrate A, which is represented as A, forming this product B. Here nucleophile attacks the electron deficient carbon atom or electrophilic carbon atom from the opposite side of the leaving group, forming this product. The leaving group was drawn on the right in this equation. So the nucleophile attacks from the left side. Because the nucleophile and the leaving group are in the opposite positions relative to the other three groups. Here it is methyl group, deuterium and hydrogen. On carbon, the backside attacks results in the inversion of configuration around the stereogenic carbon atom. This carbon is chiral. You can see all the four groups are different. So it is chiral or it is stereogenic. And hence there will be inversion of configuration around the stereogenic center in the product. Okay, that means the configuration of the carbon atom becomes inverted during the SN2 reaction. That is the stereochemistry of SN2 reaction. Okay, the inversion in SN2 reaction can be best described by this picture. You can see it is the nucleophile. For example, OH negative, OH negative. If it is OH negative, this red ball is oxygen, which carrying lone pair of electron and negative charge. As the nucleophile approaches the backside of the tetrahedral carbon, the substrate molecule, say for example, it is methyl bromide, it is the leaving group, it is tetrahedral in nature. As the nucleophile approaches the backside of the tetrahedral carbon, the carbon hydrogen bonds begin to move away from the nucleophile and its attacking electron. These carbon hydrogen bonds begin to move away from the nucleophile and its attacking electron. Then it is the transition state. You can see the carbon hydrogen bonds in the transition state are all in the same plane. The carbon hydrogen bonds are in the same plane and the carbon is pentacoordinate. You can see the center carbon atom have 5 bonds, but all the carbon hydrogen bonds are in the same plane rather than tetrahedral. Okay, then you can see the bonds between carbon and the leaving group is in the process of breaking, and the bond between the nucleophile and the carbon is in the process of formation. Then in the product you can see the carbon hydrogen bonds actually in the transition state have continued to move in the same direction, that is away from the nucleophile. When the bond between carbon and nucleophile is fully formed, when it is fully formed, and the bond between carbon and bromine is completely broken, bromide is eliminated. Carbon is once again tetrahedral, it becomes tetrahedral, but with inverted configuration of the first substrate molecule. You can see the configuration gets inverted by this process, and it is the inversion of configuration in SN2 reaction. So the most distinctive characteristic of an SN2 reaction is the inversion of configuration of the electrophilic carbon in the transition structure. That means SN2 reactions are stereospecific in nature. And this stereospecificity can be established, or it was established by the experiments with optically active substrate which are chiral at the reaction site. For example, the reaction of R2-bromobutane with hydroxide yields S-butan-2-ol or S2-butanol, while the S substrate gives R product. See, it is R substrate which gives S product. Here the OH negative ion, that is the nucleophile, attacks this chiral carbon atom. Its configuration is R. See, it is R2-bromobutane, which on SN2 reaction with the nucleophile, inversion of configuration takes place to form S2-butanol or S-butan-2-ol. That is the stereochemistry of SN2 reaction. See, similarly, cis-1-bromo 4-methyl cyclohexane. It is a cyclic compound and it is called cis. Both the methyl group and bromine are on the same side. That is why it is represented as cis. Cis-1-bromo 4-methyl cyclohexane, which on nucleophilic substitution reaction with the OH negative ion or this anion, bromide is, or this leaving group gets departed from this carbon atom and thereby form trans 4-methyl cyclohexanol. The configuration of this carbon has been inverted. Okay, that much about the stereochemistry of SN2 reaction. Now let us consider the factors that influence the rate of SN2 reaction. The rate of an SN2 reaction depends upon 4 factors. They are the nature of the substrate. That means the bulkiness of the alkyl halide. Usually alkyl halide gives SN2 reaction, and the nature of this alkyl halide affects the rate of SN2 reaction. How do the nature of SN2, the nature of substrate molecule affects the SN2 reaction? That can be discussed. Then the next factor that influence SN2 reaction, rate of SN2 reaction, is the power of the nucleophile. And the third factor is the ability of the leaving group to leave. And the last factor, the nature of the solvent. These are the 4 important factors that affects the rate of SN2 reaction. We can discuss each of these factors in detail. First, let us see how the nature of substrate molecule affects the rate of an SN2 reaction. See, an unhindered alkyl halide, that means those in which the backside of an alpha carbon is not blocked, will react fastest in SN2 reaction. That is, unhindered alkyl halides, that means those in which the backside of the alpha carbon, where the nucleophile has to enter to the electron deficient or electrophilic carbon of the substrate molecule, is not blocked, will react fastest in SN2 reactions. That is why methyl halide gives the fastest reaction than primary alkyl halide, which in turn will give faster reaction than secondary alkyl halide, which in turn give faster reaction than tertiary alkyl halide. That means methyl halide gives the fastest SN2 reaction, and the tertiary alkyl halide usually gives the lowest, or it is the slowest rate in SN2 reaction. That means while a methyl halide reacts quickly in SN2 reaction, a tertiary halide does not react. The backside of an alpha carbon in a tertiary alkyl halide is completely blocked. The backside of an alpha carbon atom in a tertiary alkyl halide is completely blocked for the attack of nucleophile. Okay, influence of the structure of substrate molecule can be better understood by using this picture. You can see the bulky substituents attached to the carbon that undergo backside attack decreases the nucleophilic access to the backside of the carbon, and therefore decreases the rate of reaction. This explains why, as the size of alkyl group increases, the rate of the substitution reaction decreases. You can see here from left to right the steric hindrance of the bulkiness or the substituent attached to the electron deficient carbon atom diminishes the accessibility of the nucleophile to the electrophilic carbon atom. You can see from methyl bromide to tertiary butyl bromide, this access continues to decreases. Thereby, the rate of SN2 reaction continues to decrease from methyl bromide to tertiary butyl bromide. Methyl bromide to the primary alkyl halide, for example, ethyl bromide, then secondary alkyl halide, that is 2-bromopropane, and then tertiary butyl bromide. Methyl bromide gives fastest reaction, whereas tertiary butyl bromide gives no SN2 reaction at all. Now let us consider how the nucleophilicity of a nucleophile influence the rate of an SN2 reaction. The rate of SN2 reaction, or the kinetics of SN2 reaction, depends on the concentration of both the nucleophile and the substrate molecule. So that nucleophile involves the rate determining slow step of SN2 reaction. Better the nucleophile, the faster will be the rate of SN2 reaction. See, the table shows which are weak nucleophiles and which are good nucleophiles. See, bisulfate ion, this dihydrogen phosphate ion, then carboxylic acid, and all these nucleophiles are very weak nucleophiles. Weak nucleophiles: alcohol, water, nitrate, then fire, fluoride, chloride, carboxylate, ammonia, dimethyl sulfide. A good nucleophile: azide, bromide, hydroxide, methoxide. These are good nucleophiles. See, azide, bromide, hydroxide, and methoxide are good nucleophiles, whereas very good nucleophiles are cyanide, thioalcohol, sulfides, trimethyl phosphide, amide, Grignard's reagent, iodide, and hydride. All these are very good nucleophiles. Okay, and so we can say, as the nucleophilicity of nucleophile increases, the rate of SN2 reaction increases. Right? Nucleophilicity is usually affected by the steric effect. Nucleophilicity is affected by steric effect because a bulky nucleophile cannot approach the backside of the carbon as easily as less sterically hindered nucleophilic can. That means nucleophilicity is affected by steric effect. As the bulkiness of the nucleophile increases, they cannot approach the backside of the carbon as easily as less bulky or less sterically hindered nucleophile can. But as far as the basicity of a nucleophile is concerned, Basicity, on the other hand, is relatively unaffected by steric effect because a base remove an unhindered proton. Usually, a nucleophile can act as a base also. Okay. See, for example, in this case, ethoxide ion is a better nucleophile than tertiary butoxide. It is a bulky nucleophile. This bulky nucleophile exert a steric hindrance on approaching the backside of the electrophilic carbon atom, while this ethoxide ion is not sterically hindered, can easily approaches the electrophilic carbon atom. Therefore, tertiary butoxide with its 3-methyl group is a poor nucleophile than ethoxide. But the tertiary butoxide is a stronger base, than ethoxide. Okay. Now let us consider how the leaving group affects the rate of SN2 reaction. See, the leaving group usually has a negative charge. Group which stabilize a negative charge are best leaving groups. That is, the weakest bases are stable as anion and are the best leaving groups. Weak bases are readily identified. They have high pKb values. See this table. This iodide having highest pKb value, that is about 30,000, whereas NH2 having pKb value 0. So it is the weakest base, and so best best leaving group among these groups, such as bromide, chloride, fluoride, hydroxide ion, alkoxide ion, and amide ion. And this iodide ion is the best leaving group because it is least basic in nature, whereas amide ion is its basicity is very high. The pKb value is equal to -21, and hence it is the poorest leaving group. See, from right to left, the leaving ability of these groups increases. So iodide is a good leaving group because iodide is non-basic. We can say this iodide is non-basic. It is the conjugate base of the strong acid, hydroiodic acid. So it is the weakest base. Then OH negative and NH2 negative are poor leaving group because they are strong bases. OH negative, NH2 negative, OR negative, all these are strong bases and hence poor leaving groups. Okay. So the relative reactivities of alkyl halides in an SN2 reaction can be represented like this. These are the alkyl halides: alkyl iodide, alkyl bromide, alkyl chloride, and alkyl fluoride. See, alkyl iodide will be most reactive alkyl halide in SN2 reaction, and alkyl fluoride is too unreactive to undergo an SN2 reaction. Then consider some of the examples. Which alkyl halide is more reactive in an SN2 reaction with a given nucleophile? See the first example. It is 2-bromopentane and it is 2-methyl 1-bromobutane. See the difference. It is a primary alkyl halide and it is secondary alkyl halide. Both the leaving groups are same, and hence we can say the substrate as a whole, and so it is a primary alkyl halide and it is a secondary alkyl halide. Primary alkyl halide is more reactive than secondary alkyl halide in an SN2 reaction. So this alkyl halide is more reactive than this alkyl halide. And in the second example, you can see both are secondary alkyl halide. The difference is in the leaving group. Here it is bromine and it is chlorine. Bromide ion is less basic than chloride ion. So the leaving ability of bromide is more than that of chloride, and hence bromopropane, 2-bromopropane is more reactive in an SN2 reaction. See another example. Here both are bromides, alkyl bromides, and they are secondary also. secondary alkyl bromide. But the difference is in steric influence. It is the methyl group, but here it is ethyl group. But in this case, both are ethyl group on the either side of this bromide. And so it is more strained. This molecule is more strained, crowded, and than this molecule. And hence, for SN2 reaction, as the structure of alkyl or the substrate molecule increases, the reactivity decreases. So the first molecule will be more reactive in an SN2 reaction. And in the last example, see these two examples. The first example is primary alkyl halide, and it is the secondary alkyl halide. Primary is more reactive than secondary alkyl halide in an SN2 reaction. So the first molecule is, more reactive than the second molecule. Okay. Now let us discuss the effect of solvent on rate of SN2 reaction. You know, there are three types of organic solvents: the protic solvent, polar aprotic solvent, and non-polar solvent. Polar solvent usually contains OH or NH2 groups. Usually polar solvents slow down SN2 reactions. Polar aprotic solvents like acetone, which contains strong dipoles, but no OH or NH2 groups. Polar aprotic solvent usually speed up SN2 reactions. Another class of organic solvent is non-polar solvent like hydrocarbons. SN2 reactions are relatively very slow in non-polar solvent. Okay, the important examples of protic solvent: water, methanol, ethanol, and acetic acid are the important examples of protic solvent. These protic solvent form a cluster around the nucleophile, or the protic solvent solvate the nucleophile and lower its energy. Thereby it gets stabilized and reduce its reactivity via hydrogen bonding. Thus, a solvated anion, here it is nucleophile, it is the here X is the nucleophile which gets solvated by alcohol, methanol, ethanol, as the case may be, has reduced nucleophilicity and reduced reactivity and increased stability. Thereby, because of this increased stability and reduced reactivity and nucleophilicity, such a nucleophile which gets solvated, or in presence of protic solvent, the nucleophilicity of anion gets reduced. Or we can say a solvated nucleophile has difficulty hitting the alpha carbon atom. Okay, then see how do the polar aprotic solvent influence the nucleophilicity. See, the important polar aprotic solvents are acetonitrile, acetone, dimethyl formamide, dimethyl sulfoxide, hexamethyl phosphoramide, and dimethyl acetamide. Usually, the polar aprotic solvent solves the cation counterion, not the nucleophile. The polar aprotic solvent solves the cation counterion. Thereby, the nucleophile become free. See, for example, sodium acetate in presence of methyl cyanide. Here the cation counterion is sodium ion of the nucleophile acetate ion. Here this cation counterion sodium gets solvated by this methyl cyanide, whereby the nucleophile acetate become free. So polar aprotic solvent solves the metal cation, leaving the anion counterion or nucleophile bare, and thus it becomes more reactive. Okay, that is how the polar aprotic solvent influence the nucleophilicity. The non-polar solvents like benzene, carbon tetrachloride, or hexane do not solvate or stabilize nucleophile. Usually SN2 reactions are relatively slow in non-polar solvents, similar to that in protic solvents. For example, benzene, carbon tetrachloride, normal hexane, all these are nonpolar solvents, or SN2 reactions are relatively slow in these nonpolar solvents. Okay. Thus, SN2 reaction requires a polar aprotic solvent. Okay. Now let us discuss the next type of nucleophilic substitution reaction, nucleophilic substitution, unimolecular reaction, or SN1 reaction. For example, the tertiary alkyl bromide, for example, tertiary butyl bromide, here it is tertiary butyl bromide, or any tertiary alkyl halide, which on treating with the solvent water, forming tertiary butyl alcohol, the corresponding alcohol is formed. This reaction involves the SN1 mechanism. See the mechanism of the reaction. First of all, homolysis of carbon halogen bond takes place in the right determining step. That means in the right determining step, only this substrate molecule, tertiary butyl bromide or any tertiary alkyl halide, involves homolysis of the carbon halogen bond takes place to form a more stable carbocation in the slow right determining step. And the next or fast step, nucleophile, here it is water or any solvent, adds to this carbocation, forming a protonated alcohol. Then in presence of water, excess water, deprotonation or proton transfer takes place to form the alcohol, tertiary butyl alcohol. It is the mechanism of SN1 reaction. That is, in the right determining step, homolysis of carbon halogen bond from the tertiary alkyl halide take place to form a more stable carbocation. Here it is tertiary butyl carbocation. And the next fast step, addition of nucleophile into this tertiary butyl carbocation takes place, forming protonated alcohol. And from this protonated alcohol, proton transfer to water molecule takes place, forming the product tertiary butyl alcohol. It is the mechanism of SN1 reaction. Okay, here the right determining step involves only the substrate molecule, and hence it is a first order reaction. That means SN1 reaction is a first order reaction. You can see tertiary alkyl halides are essentially inert to substitution by SN2 mechanism because of steric hindrance. But despite this steric hindrance, tertiary alkyl halides undergo nucleophilic substitution reaction quite rapidly, but by a different mechanism. That is what is called, that we had seen as SN1 mechanism. But usually tertiary alkyl halide undergo nucleophilic substitution by SN1 mechanism. SN1 means substitution, nucleophilic, first order or unimolecular reaction. It obeys first order kinetics. That means right is equal, that the rate of reaction can be represented like this. Right is equal to the rate constant into concentration of alkyl halide or the substrate molecule only. That is why it is a first order reaction. That is, the rate of reaction is proportional to concentration of substrate molecules only. That means the rate depends upon the concentration of only one reactant, that is the alkyl halide, not the nucleophile. The order of reactivity of substrate for SN1 reaction is the reverse of SN2. See, it is the order of reactivity. It is actually the reverse of SN2 reaction. Here the tertiary alkyl halide, the reactivity order is tertiary alkyl halide is most reactive. The reactivity is greater than secondary alkyl halide. The reactivity of it is greater than primary alkyl halide, which in turn greater than vinyl halide, then phenyl halide, then methyl bromide or methyl halide. It is the the reverse is the increasing order of SN1 reaction. Here, from right to left, the rate of reaction increases. Okay, now let us discuss the stereochemistry of SN1 reaction. See, it is a tertiary alkyl halide which on solvolysis forming the corresponding alcohol. If we examine the mechanism, first of all, in the rate determining step, homolysis of carbon halogen bond from the tertiary alkyl halide take place to form a more stable carbocation. It is tertiary carbocation. You know the nature of tertiary carbocation. It is this carbon is sp2 hybridized and hence it is planar in nature. So the nucleophile, the solvent molecule water, can attack from either side, from the front side or from the back side. If the nucleophilic attack to the electron deficient carbon atom, this electrophilic carbon atom takes place from the front side, then we will get an alcohol with retention of configuration. With retention of configuration, if the nucleophilic attack takes place from the front side. Similarly, if the nucleophilic attack takes place from the back side of this positively charged carbon atom, then inversion of configuration takes place. Thereby, we will get this alcohol. Configuration gets inverted because of the attack of nucleophile, solvent nucleophile take place from the back side. That is why this inverted configuration, molecules with this inverted configuration is formed. So we will get both the molecules, a mixture of alcohols with retention of configuration and inversion of configuration. But usually in SN1 reaction, the molecules with the inverted configuration is obtained more than the molecules with the retention of configuration, because as the front side attack or takes place, it gets partially impeded by the presence of outgoing bulky leaving group. Here the bromide ion is bulky, or sometimes it may be iodide, the leaving group iodide or bromide or any such anion is bulky in this case, and this bulky leaving group partially impede the attack of or the moving of the nucleophile towards the electrophilic carbon atom. That is why we get an alcohol with inverted configuration more than the alcohol with retention of configuration. That is the stereochemistry of SN1 reaction. That is racemization. We get the both the alcohol, that is alcohol with retention, configuration of retention, and with the configuration of inversion. We will get this mixture. But the inverted alcohol with the inverted configuration is obtained as the major product in this case, because the leaving group partially impeded the attack of or moving of the nucleophile towards the electrophilic positively charged carbon atom. That is the stereochemistry of SN1 reaction. So we had seen that in SN2 reaction, inversion of configuration, only the inversion takes place, but in SN1 reaction, both the retention and inversion both are take place. That is why we will get a racemic mixture. From the racemic mixture, the molecule with the inverted configuration is obtained as the major product. Okay, that is the stereochemistry of SN1 reaction. Now let us discuss what are the important factors that influence the SN1 reaction. There are three factors that affects the SN1 reaction. The nature of the substrate molecule, that means the nature of alkyl halide, the ability of the leaving group, and the nature of the solvent. These are the three important factors that influence the SN1 reaction. Usually the rate of SN1 reaction is independent on the concentration of the nucleophile. As you know, the nucleophile doesn't take part in the rate determining slow step. Okay, how do the nucleophile influence rate of SN1 reaction? You know, the nature of nucleophile has no influence or no effect upon the rate of SN1 reaction. because the slowest rate determining step is, the dissociation of the leaving group and formation of carbocation. There is no involvement of nucleophile in the rate determining step, and hence the nature of nucleophile having no effect upon the rate of SN1 reaction. See, all the carbocations are very good electrophiles. They are electron acceptors, and even weak nucleophiles like water, methanol, these are solvent, will react quickly with them. Then we can discuss the effect of nature of the leaving group on the rate of SN1 reaction. The nature of leaving group has the same effect on both the SN1 and SN2 reaction. The better the leaving group, the faster a carbocation can form, and hence faster will be the SN1 reaction. The leaving group usually has a negative charge. Groups which best stabilize this negative charge are the best leaving group. That means the weakest bases are stable as anions and are the best leaving groups. Weak bases are readily identified by their high pKb values. See this table. Iodide has highest pKb value 23, and the amide has the lowest pKb value minus 21. That is why iodide is the best leaving group, and NH2 group, in this table you can see the NH2 group is the poor leaving group. It is the from right to left will be the increasing leaving ability. From amide to iodide, you can see the leaving ability gets increased, and hence iodide will be the best leaving group while amide will be the poor leaving group. Then let us see how do the solvent affect the rate of SN1 reaction. For SN1 reaction, the solvent affects the rate only if it influences the stability of charged transition state, that is carbocation. The first rate determining step of the SN1 reaction involves the formation of carbocation. Any factor that stabilizes the carbocation will increase the rate of SN1 reaction. And in this case, any solvent that increase the stability of carbocation increase the rate of SN1 reaction. Usually polar protic solvents like water, methanol, ethanol, ammonia, tertiary butanol, acetic acid, etc. will solvate and stabilize the charged transition state or the carbocation intermediate, therefore lowering the activation energy of the carbocation and accelerating SN1 reaction. See, it is the solvation of this carbocation by alcohol. Okay, one of the important characteristic of SN1 reaction is SN1 reaction usually involves the rearrangement reaction, because the rate determining step involves the formation of a more stable carbocation. If there is a chance for a more stable formation of more stable carbocation from a less stable carbocation formed during the SN1 reaction, either through hydride shift or through an alkyl shift from the adjacent carbon atom, it will form a more stable carbocation. And after that, the nucleophilic attacks takes place to the more stable carbocation, forming the product. Here see, it is a secondary alkyl halide. Upon treating with this solvent methanol, which acts as a weak nucleophile, first form a secondary carbocation in the rate determining step. But you can see the adjacent carbon atom or the carbon atom attached to this secondary carbocation is a tertiary carbon atom which containing a hydrogen, and through hydride shift from this tertiary carbon atom to the secondary carbocation, this tertiary carbon atom becomes tertiary carbocation. That is why this rearrangement takes place via hydride shift to form this tertiary carbocation. After the formation of tertiary carbocation, the nucleophilic attack takes place to the tertiary carbocation, in the second step, forming this protonated alcohol first, and then proton transfer to the methyl alcohol takes place, forming the product. Okay, that is the rearrangement reaction usually taking place in SN1 reaction. This is an example of rearrangement containing methyl shift. This molecule, upon treating with water, which is a weak nucleophile, in presence of isopropanol, we get this alcohol. In the right determining step, a bromide ion, the leaving group bromide ion departed, forming a secondary carbocation. But you can see the adjacent carbon atom or the carbon atom attached to this secondary carbocation is a quaternary carbon atom. It is a quaternary carbon atom. Thereby, a methyl group can easily shift to this secondary carbocation to form a more stable tertiary carbocation. Thereby, you can see this methyl group shifted to this positively charged carbocation. Thereby, this carbon becomes tertiary carbocation, a more stable carbocation. And then in the next or fast step, the second step of the SN1 reaction, water, which is the nucleophile, weak nucleophile, which attacks this tertiary carbocation, forming a protonated alcohol first, and then proton transfer to the water molecule, forming the product alcohol. It is an example of rearrangement involving methyl shift. Okay, see, I have already discussed what is SN2 reaction, what is the mechanism of SN2 reaction, what is its stereochemistry, what are the important factors that affects the SN2 reactions. Then come to SN1 reaction. What is SN1 reaction? What is the mechanism of SN1 reaction? What are the important factors that affects the SN1 reaction? How the rearrangement affects the nature of the product in SN1 reaction, etc. Now you might have got a clear idea and concept of SN1 reaction and SN2 reaction. I conclude this video here. Thank you for watching. Thank you.